Okay, thank you for having me, Michael. It's an honor to speak in front of you guys. So I'm going to build on Aniket's great talk and background on blockchain. So I won't get too much into the general motivation, but generally speaking, as most of you know, blockchain was introduced in 2008 by Satoshi Nakamoto. And the relation between Bitcoin and blockchain is that blockchain is the technology, the platform above which Bitcoin is implemented. And mainly blockchain is an engineering breakthrough. It uses primitives that were known by then, but Satoshi Nakamoto tailored them in a very novel way to create blockchain. And perhaps there are other applications. We spoke about it before. And if you're following what happened to the market in the last weeks, then in the beginning of May, the market cap of cryptocurrencies was about $30 billion. And since then, it tripled. And more, it's now over the $100 billion. It's kind of a hot topic now. But unfortunately, there are great problems to this system. So generally, the motivation for this work is that blockchain doesn't scale. Bitcoin specifically processes about 7 transactions per second. Other systems have dozens of transactions per second. But that's around the order of magnitude of throughput, TPS. That's the formal throughput measure. And if you're following the community, the online community, in the Bitcoin community, you'll know there's a heated debate in the community between the miners and the core devs. The miners are pushing for large throughput, for big blocks. Of course, they want more revenue, so larger throughput means more revenue for the miners. And then the core devs were much more security-oriented. They fear that the system will break apart or be compromised if you have large throughput. And so I chose this picture. If you know how the community is now, the dynamics, this is not over-dramatic to imagine Bitcoin as this slow and heavy truck that's on the verge of falling from a narrow cliff. There's also conflicts and peace talks and agreements they're signing. Coming September, they should initiate the New York Agreement, if you know what I'm referring to. So there are really political factions here. Okay. So the general agenda of our research is, first of all, to understand better the scalability-security trade-off of blockchain. That's perhaps previous work. And then understand whether this trade-off is inevitable or not. Then we want to design better systems that alleviate this trade-off and are scalable. And I should mention that these works are not just theoretical. They're practical, developer groups in the industry that really want to implement these protocols. So this is not just theory. So the main agenda is breaking the chains of blockchain protocols. Okay. So as you heard, the high-level design of blockchain is the replicated state approach, the replicated ledger approach. Whenever there's a transaction in the system, instead of informing only the bank or a central entity, you publish it to everyone in the network, and they maintain a local copy of this transaction. And they embed transactions, new transactions in the ledger, and the transaction ledger essentially represents the state of all valid transactions in the system. And just remember, for the remainder of the talk, sorry, the time here flows from the left to the right. It's a bit confusing. The pointers are from the right to left, but this is the first block in history, and then the last block in the history is on your right. Okay. Last comment, there are 2 types of nodes in the network. There are active nodes, which are always online, full nodes or minor nodes, and they're in charge, responsible on extending the ledger. And there are also user nodes, which only plug into the network whenever they need to. Okay, so in general, what's the main observation regarding blockchain? So we observe that the blockchain structure is robust only because it really comprises a single chain. So when the throughput is low, meaning you process only several transactions per second, say 10 transactions per second, then you have low frequency of blocks. In Bitcoin, it's 10 minutes. And then you can say that network delays are negligible. And when they are negligible, then the longest chain rule is really a good rule. So Anik had showed you the longest chain rule. If there will be other blocks here that are not part of the longest chain, they will be discarded. And the blockchain, in peace days, in normal behavior of the system, the next block will extend the longest chain. We have enough time and we're slow. That's how Bitcoin is secure nowadays. However, if you want to increase the throughput, you can either create more frequent blocks or create larger blocks. But in either case, you'll end up having much more blocks that are not created on top of the longest chain. Okay, so the red blocks here are blocks that honest, innocent miners created. Didn't have an updated worldview regarding the state of the longest chain. So they created these blocks in parallel to the longest chain. And the longest chain rule dictates that these blocks should be discarded and ignored. And in particular, all the transactions in them are ignored. So this is also a waste. This is both a waste of throughput and of security. These blocks contribute nothing to the protocol according to the Bitcoin protocol. Okay? So essentially what happens, let's say I'm a miner, I'm in the miner faction and I want to push for 100 megabyte blocks, a large throughput. Then the core devs, the security-oriented guys will say, you know what, if we'll increase the blocks, increase the throughput, we'll have much larger orphan rate, and we'll have a waste, and we'll be much more compromised to manipulations by attackers. So that's the general trade-off we are reaching. Okay, so to see this on the high level, there are three phases to the three possible phases to the transaction throughput in Bitcoin. Today, Bitcoin is in the safe green zone where there's very modest throughput and the protocol is secure. It's in the order of magnitude of tens of transactions per second. Then in the red zone, you have the extreme throughput of hundreds of thousands of transactions per second, which the network will probably won't be able to support. And we are aiming at somewhere in between. I'm not sure exactly where, but in the high throughput zone where you process thousands of transactions per second, maybe tens of thousands of transactions per second, and the protocol. But here, the Bitcoin protocol is insecure.
So when you say the network is congested, suppose that there was a security solution, what does it mean for the network?
That nodes their buffers are exploding. So if nodes
because of processing power?
No, because if you have hundreds of thousands of transactions per second, they're in regular nodes. I mean, you don't want to assume that if you have designated nodes that are really powerful, of course they can process hundreds of thousands of transactions per second. But if you want a decentralized system that also weak players can participate at, then they won't be able to process this volume. So a transaction is typically a half a kilobyte. So this would imply 50 megabyte per second. So you can support it if you want, but then your honest nodes are a strict subset of what you had before. So again, the yellow zone is what we want to eliminate. We want to reach this zone, this state where you can support whatever the network supports. But today in Bitcoin, that's not the case. You suppress the throughput in order to maintain the security. And just for comparison, a Visa processes tens of thousands of transactions per second. So in peak times, even more. But that's the area we want to get at.
Wait, I think the green zone can you go back. Here, still the protocol is still insecure. So when you're saying,
yeah, that's a typo. I mean, yeah, the
goal is.
Thank you, Or. What?
The goal is for it to be secure. I mean, current Bitcoin will not.
Yes. Okay. I'll wait further comments from you. Okay, so the outline of the remainder of this talk is as follows. First, I wanted to describe the correct framework for layers of blockchain. So this is just my view of how to divide the blockchain system into layers. And this is deliberately different than Bitcoin's design or a conceptual design of the system. And then I will show how Bitcoin, because it deviates or it didn't follow this agenda, then it has the scalability problem. Then we will zoom into the consensus layer and speak about what should a consensus layer, how does it look like in this framework. And finally, I want to present the Spectre consensus protocol, which our team here invented. And Spectre alleviates this trade-off and is scalable. It's in the green zone without the typo. Okay, so here's a crude division of a blockchain into layers. It's just, I'm flexible with the namings, the titles, but in general, you have the network level, that's the bottom layer, and the data layer, and then the consensus and application layer. So the network layer is perhaps the simplest layer. It's where the network lives, network node lives. It's a peer-to-peer network. And then there's the transaction, where the data layer with the ledger is formed, the transaction ledger is formed. And here, in our paradigm, the transaction ledger still could have conflicts. There's no consensus mechanism. There's no conflict resolution, just a simple ledger. And then in the consensus layer, this ledger is organized and ordered. Okay? And the consensus protocol is an abstract procedure which really is part of the application layer. And just it's good for my business to call it a separate layer because I invested time in consensus protocols. But it's really just part of the first procedure that an application runs. And then in the final layer, the application layer, there's economic meaning. There's meaning from extracting meaning from this ordered ledger. So to give this a more precise description, let's take an example. So assume Alice and Bob wanted to transact. So how will this correspond to the layers? So let's say Bob wants to pay Alice. So they will both plug into the network. And then Bob will publish the transaction. This is the data which is discussed in the network. It will publish the transaction. Then some miner in the data layer will collect this transaction and embed it in some block in the ledger. But this still does not mean the transaction is valid in our paradigm. And then Alice's wallet will begin with listening to the ledger and putting the corresponding block in its correct location within the ledger. And then the wallet will tell Alice whether the transaction is valid or not. Okay, so again, first you plug into the network, you publish a transaction, the transaction is embedded in some block, then the block is given an order, a location in the ledger, and finally, reading this location, you interpret whether the transaction is valid or not. Okay, and now I will get to this in more detail. Okay, so again, the simplest layer is the network layer. It's the peer-to-peer decentralized network in the blockchain system. The topology is unregulated, dynamic, no one knows it. It keeps shifting. And some nodes are always online, the full nodes, the miners, and some nodes plug in whenever they want.
The word anonymous here, you mean?
That you don't need to declare identity in order to gain access to the network, and you don't need to say who you are. It's not in the strict sense of, it's just to distinguish it from permission setup. Okay. In the data layer, users push transactions to the system, and miners collect it and pack it into blocks and publish these blocks. So here there's several transactions that users just suggested to the network. They want the network, the miners to confirm it, and then miners pack them in blocks in whatever order they decide to. And briefly going over the mining process, Aniket mentioned it before. So block creation requires heavy computation. This computation is deliberately wasteful. It has no other purpose other than wasting the miner's resources, computational resources. And the block contains a proof, a short proof, that indeed it wasted computation in the sense that it solved a difficult to hard crypto puzzle. Okay, so this is the proof of work. So apart from having transactions in the block contains a proof that it wasted resources on average. Okay, and this counters a Sybil attack, where a miner can create multiple identities. So now we don't think of a miner as, we don't count a miner's power by counting how many nodes it created, but rather how much computational power it controls. Okay, so going more into the scalability issues in the data layer. So block creation is regulated by the protocol. There are two hard-coded parameters that are still connected to the data layer, to the block mining process. One parameter is the block size. So we assume there's a hard-coded parameter that says what's the upper bound and allowed upper bound on the block size. And the second hard-coded parameter is the puzzle difficulty, how difficult it is to create a block. So this is essentially the target that Aniket described, the target, how many zeros essentially you need to hash into. But that's more detail. The high level is what's the block creation that we are aiming at. So the creation rate that we're aiming at in Bitcoin is one block per 10 minutes. And specifically one block of 1 megabyte, which is roughly 2,000 transactions. Okay, so there are some different versions of the protocol, but generally this becomes between 3 and 7 transactions per second. And notice that these parameters, which they dictate the scalability, the throughput of the system, right? They dictate how much transactions you process per second. These parameters belong to the data layer. They are part of the mining protocol, not of the consensus protocol. Okay, this will prove a crucial distinction. Okay, finally, how are blocks structured? So the first stage of structuring a block, the first step is every block has to contain a pointer to previous blocks. Okay, and this pointer is essentially information that this block came after the blocks it points at. So here the big block on the right, he has 3 pointers to previous blocks, and these pointers represent the fact that this block was provably created after these blocks. Of course, it couldn't have been created before them, because then the miner couldn't have known how to point into these blocks. So the pointer here is not a real pointer to the memory because it's a replicated structure. It's rather the hash ID, the hash of the previous block, which functions as a unique ID. Okay, so in the header of the block, there's a list of the hashes of previous blocks. And importantly, this is not the way Bitcoin works. This is part of our paradigm to think of a scalable blockchain. And because these pointers are representing information about the time precedence of blocks, it's really important, or ideally we would have wanted these pointers to be the block to point at as many possible previous blocks as possible. Okay, we would like, ideally, if this miner that created that block had all the information needed, we would want him to point at all blocks that were created beforehand.
What is the advantage of linking directly to all blocks rather than linking to blocks, one block which link to the next one?
So I'll get to this now. So concretely, the mining protocol here in the data layer, the first rule would be to point at all previous blocks, but not at all, of course, just on those that weren't previously pointed at. So here's the new block. he points only on these two blocks because they weren't pointed at previously.
Okay, you just said we would have preferably wanted to point at all blocks, but you want just these that are not indirectly blocked.
Yeah, so what I mean is we prefer to have as many information as possible.
Yeah, of course.
Yeah. It sounds trivial, but in Bitcoin you don't do that, right? In Bitcoin you omit.
I just thought maybe there's an efficiency advantage in also.
Okay. Fine. Okay. So the mining protocol, the first rule would be simply you should embed pointers to all the blocks that weren't pointed at before. This is the rule number 1. Rule number 2: publish your block as soon as possible, as fast as possible. Okay. So these are the two extremely simple mining instructions in our paradigm.
Just clarify. The rule 2 is also present in Bitcoin, right?
Yes.
Okay.
Yes. The important thing to observe here that we are not asking the miners to run any consensus mechanism. They do not need to reason about the transactions in these blocks. They do not need to check whether they're conflicting or not. They're just mining. You can think of it as a dummy machine. They're just mining as fast as fast as the network can support, and they do not mind at all about the contents of these blocks. That's why these rules are much simpler than Bitcoin in the sense that a miner doesn't need to know anything almost.
But what about the difficulty?
Yes. So the difficulty I pushed aside. The miner does need to know how to mine a block. Yeah, you're right. So we need to adjust it like Bitcoin does. So the mechanism would be simply, I don't want to get into it, but in short, like Bitcoin does, right? Bitcoin just measures how long it took you to create 2016 blocks in your chain, right? So in this paradigm, it will be in your past. It's just a simple generalization of Bitcoin's difficulty adjustment.
Sure, but just you can't really separate the layers.
This layer has nothing to do with the contents of this block. It's just with the headers of the block, right? You just need to know how many blocks were created, were mined. It doesn't need to know whether the contents were valid in a more meaningful way.
But if let's say a miner published a block with two conflicting transactions,
yes,
wouldn't he get a disadvantage? Why would he want to do that? I mean, the block wouldn't be accepted.
In our paradigm, it will. And now I will get to it now.
They become basically repeaters.
Miners,
in this new definition, are repeaters. They repeat the broadcast
yeah, but
the message go through.
Yes, with some throttling of the messages using proof of work.
Still proof of work?
Yes.
Okay.
Yes. So.
No, but
that's the old word.
No.
Yeah. So I said we still have in the data layer the proof of work, which it makes blocks difficult to create. But the difference is that they don't need to know much more than that in order to create a block. Okay. So pushing forward. How does the layer look like? How does the ledger look like in the data layer? Like a directed acyclic graph, a DAG. So this is our generalization over the blockchain. We envision a block DAG. And this is the first block in history. Again, the time flows from the left to the right. And at your right, there's the new block. And assuming this is the DAG it currently locally observes, this is assuming all the black blocks represent the entire set that this miner observes currently, he will embed pointers to all three leaves of this block.
Okay, so essentially you would say that what Bitcoin is doing is just a special case of that, and therefore it's right?
Well, if there's a fork, Bitcoin doesn't, it's a special case only if there's happen to be only one chain, right? But if there's two chains, Bitcoin doesn't point at both. Bitcoin allows you only to point at the winner, at the single winner of the.
Right, of course. But what I'm saying, the chain in Bitcoin is, of course, also a DAG. It's just the trivial case.
Yes.
So, so essentially, you're saying that because Bitcoin is combining this consensus of and this place forming. So
Yeah, so it's not a totally new paradigm I'm presenting here. It's just a nuanced way of what comes before what, the consensus or the ledger. Yeah, so it really follows most of Bitcoin's primitives and line of thought. Nonetheless, there are some important differences in when you also point at off-chain blocks, even in Bitcoin. The reduced cost for attackers and such. I don't want to get into it. Yes, but that's a correct comment. I think it's my next slide, actually. Yes.
So one question I think that is clear to so there are sometimes some on the previous slide.
Yes.
Some nodes have two arrows which are pointing to them because those two new blocks were not knowing about the existence of other block.
Yes.
That's why that one output block got pointed to something.
Yeah, so that's a good comment. So the width of the DAG is a function of the block creation rate and block size. So if on average in one unit delay you create 5 blocks in parallel in the network, then you will have an average width of 5. These blocks didn't hear about one another when they were created.
Yeah. I know that you want to talk about that later, but what is your unit of delay? You mentioned this unit, right? So how you define that? That depends upon your network, right?
Yes. So I will want to talk about it later.
Okay, that's fine.
But yeah, but the important thing, miners are agnostic to this unit of delay. That's important.
Oh.
That's the main achievement. We don't want miners to suppress themselves to maintain some bound on this unit of delay. Instead, the users, the wallet or the application layer, will observe this DAG externally and will assume some bound on the network delay, on the network unit of delay. But the miners themselves do not need to consider that. They only need to consider the network capacity. How much can the network support? This is the main goal we set out to achieve. And following up your comment, yes, so this is a generalization of Bitcoin's method. When the network delays are negligible, then honest miners have create a chain, and then the next block will probably know about all previous blocks, and therefore it will extend the chain. Okay? Of course, there are some differences when attacker tries to fork, but that's the main idea. Okay, so how does the consensus layer defined, or how does it precisely look? So the main thing you need to achieve when you have a DAG is a linear order over the blocks in the DAG. Okay, that's the definition of the consensus protocol in our framework. You just take as input a DAG and output a linear order over its blocks. And
that should be consistent with our previous linear orders. You cannot reorder.
You complete the partial order.
Yeah, exactly.
So I would think of it as a feature you can decide to implement, and we also decided to implement. But I'm not sure it's a prerequisite to define the framework. But I agree. The only reasonable orderings will be topological. Will comply with the DAG topology. Okay, so again, it's not a real separate layer. This protocol is run locally at the application, which observes the ledger, and it's sort of a consensus protocol that's no one interacts with.
I wish to disagree with you, because if you will not preserve the partial order, you can get into a situation where a bad miner can actually support situation of double spending.
Yes, so that's
that would not be not something you want.
No, so there's desire.
But if you allow
But
to
not
break
for
the
long.
partial order, no, not for exactly for long, forever, because you will burn it. You'll actually allow him. If he's colluding with a double spender,
Yes.
then I'm paying Yossi, and then I'm paying you, but then I get it into the wrong blocks, right? And I'm cooperating with the miner, and then the miner is signing once the consensus is also giving preference to block number 7, then actually I'm paying Yossi, and then you get, and then Yossi gets the money, And you
Yeah.
go.
So it's difficult for me to defend a protocol that we didn't define yet. So if someone will present a protocol that in some rare occasions doesn't respect the topology, I don't know that it will never be able to prove that this protocol is secure. I agree that it's easier to implement topological compliant protocols, but I'm not sure it's necessary to wrap this framework. But I'm flexible. It's just methodological. Okay, so the consensus protocol, the ordering protocol, should be tolerant to Byzantine nodes. And again, the Byzantine nodes are limited by their computational resources, not by the number of the nodes that they open in the network. Okay, and why do we want an agreed linear order? The reason is that it is necessary, and it is sufficient at least, an ordering to know how to interpret the transaction ledger. So, for instance, if I have two transactions in two blocks that are not related topologically, Tx and Tx bar, and you cannot co-accept them because they double spend, then you have to know which one came before which. And once you know that, you can say, okay, the first one is confirmed, the other ones are rejected. And so in this way, the application can take the ordered ledger, and reason about the status of confirmed transactions. Okay, so I hope this is clear. The ordering is equivalent to reaching consensus on the state of all confirmed transactions. Okay? Okay, so here's getting into the application layer. What I'm envisioning is that this ordered ledger will be a host of multiple protocols and multiple communities. So as Aniket mentioned, there's Bitcoin transactions, also Ethereum smart contract. Several protocols can use the same DAG fabric, and maybe even a secret encrypted protocol where some secret agents or some community of some agency wants to use this DAG in order to organize their instructions to their agents, say, and they just use the DAG to hash, to timestamp and verify their instructions, but no one knows what's in there. Okay, so this is an extreme example of how you can use several protocols on the same DAG. Every protocol the only thing it needs from the DAG is an ordering over the events in it. Once you have an ordering, those who know how to read the protocol, who are interested in reading the protocol, will have their way in the application layer. Okay, so this is like a long-term vision for how a correct blockchain should look like. Okay. Questions? Okay, so wrapping up this framework, we have the network layer, the data layer, the application layer, and the question is which layer should be responsible for restricting the throughput. So again, the throughput is technically restricted here, right? Miners create blocks in a given frequency and a given block size, but who should determine these parameters? So in Bitcoin, these parameters look to the wrong direction. They look to the consensus and they say, okay, if we use two large blocks, two frequent blocks, the consensus protocol will no longer be secure. And therefore, the entire system, the throughput here is restricted by the upper layer. And I argue that the correct way would be for the data layer to be restricted only by the network capacity. And then the application layer should work for, as long as the network is not congested and is functioning well, everything should work as planned. So this is the goal. Okay, so the scalability should depend on network capacity, not on the protocol. The protocol should not be the barrier to scalability. Okay, so the desired properties traditionally from consensus protocol are safety and liveness. Safety means that the order, in our context, that the order cannot be reversed by an attacker. And liveness means that the order between any two blocks is decided sooner rather than later. In a more familiar language, safety means you can't double spend, and liveness means that you can confirm transactions fast enough. So you can't execute a denial of service attack. Okay, so these are the two properties we want to achieve. And in a more general phrasing, you want honest blocks that good behaving blocks to not be preceded by bad blocks. And a bad block is a block that wasn't created according to the rule of having pointers to all the recent leaves of the DAG. Okay, this is a bad block, and we want good blocks to be first in the order. Okay, so let's do some warm-up of how to getting you through our research path. The first, I hid here some attacker, and I would present you the challenge of finding which chain here was mined by an attacker. Okay, so this is an easy task. The bottom line, because these blocks weren't published, right? There's no incoming links to them outside their own, and they didn't point at the DAG.
And I saw it's not just the picture.
The picture is deceiving, as you will now see. Who's the attacker now? So the picture hints that this chain is the attacker, but if you count blocks, you see that really this chain represents the honest network, and these were created by an attacker. We have here 7 blocks or so that were created on top of this block, and 8 blocks that were created atop it, and they're like separated. So if I ask you to guess which sub-DAG was mined by an attacker, so assuming an attacker has less than 50%, this one belongs to the honest nodes, and this one belongs to the attacker. Okay. Find the attacker. I should look as well. I forgot already where he is. Yeah. Yeah, okay, so here, so someone has an answer? Okay, so. No, they were created by honest miners. I know that because it didn't take too much time for this block to be published. Only like, but I'll give a more. The middle chain was created by a miner that didn't point at other blocks. It's there's no outgoing links to other blocks. This middle chain, so it's a censorship attack. There's a mining pool that only points at references its own blocks, but never acknowledges other blocks. It's a censorship attack. This is the middle chain. Okay. Finally, another hidden attacker. Where's Waldo? Now it's the top chain. The top chain is a secret chain. No one sees it. It has no outgoing links, which means that some double spend is hidden there, and the attacker waits before it attacks. It reveals it. Okay, so you see there's no outgoing links from the rest of the DAG. So all of these scenarios are what we want to capture. We want, in all of these scenarios, the blocks of Waldo to become later in the order. We don't want to allow them to proceed honest blocks in the order. Okay, so this leads us to the Spectre protocol. Spectre is a joint work with Yoad here and my supervisor, Avi Zohar. And essentially what we do in Spectre is we interpret the DAG structure as representing an abstract vote. So every block in the DAG, every block Z, has a vote whether he thinks X precedes Y or Y precedes X. And crucially, this vote is not something the miner writes inside the block. We don't ask his opinion. It's just an implicit, we use the DAG structure to reason what should be this block's vote. And the rules are essentially majority compliant. to be more specific, so some terminology, the blue blocks will be the past of Z, the green ones will be the future of Z, and these two blocks are incomparable to Z. We don't know whether they preceded it in order or succeeded it. Right, so we now want to extend the DAG topology order, as you ask us to, and provide a full order. Okay, so here's the rules of Spectre. It's a bit complicated, but I think it's understandable. So the first rule would be for all blocks that are in the future of X, that know it, that heard about it, but didn't hear about Y, they will say that X came before Y. And all these blocks, the red blocks here, they saw Y and they didn't see X, so they will vote Y precedes X. Okay? So again, if I see in my past only one block and I don't see the other, I vote that the one I see precedes the one I don't see. Okay, let's go on. Let's assume this yellow block does not see X or Y in its vote, so it will take the vote of its majority in the future. So we'll count how many blue blocks are there in its future, how many red blocks there are in its future, and we'll take the majority. So it will be colored blue, and similarly, I'm coloring here all the votes of blocks. So you see this yellow block, the reason it votes, it needs to decide whether Y becomes before X or vice versa. Then it will decide that Y comes before X. You can count that it has 5 blocks in its future that are red blocks and 4 blue blocks. Yes.
Couldn't this be dependent on the order you choose the unknown, the blocks, like the one, these ones that are decided by the future? Some might affect each other.
No, they can't, because you always look on at your future. So any topological traversal of the DAG will result in the same output. But it's a good subtle question. Okay, so again, the basic rules are vote according to the majority in your past if you see one of these blocks. But if you don't see neither, so if you see neither, then agree with the majority in your future. Okay, so it's.
But it could not be able to decide, of course. Yeah. If you have the same length. So.
What? So you can break ties arbitrarily.
You break the tie then. Yeah. Because if you break the tie, then you don't have consistency. Because I cannot. Because then.
Breaking ties is easily like doing Bitcoin, right? In longest chain, you just break ties. You flip a coin.
You have a rule for breaking ties. It's not just break whatever.
Yeah, you can use the lexicographic hash of the block. Yes. Yes. But we actually don't need. I don't want to get into details, but when you vote regarding the future blocks that you don't see, you don't really need to break ties. You can say they're even. And if you vote according to the past, if you have a past vote, then you do need to break the ties. I can explain offline why this is a correct design of the protocol, but not now. Okay, so let's see what happens just before the cascade. I pictured here the blue blocks and the red block, and what you can see here, the intuition here is that this chain of blocks wasn't published, right? It's a secret chain of blocks. And the fact that it wasn't public means that it doesn't have incoming links from honest nodes. Then assuming that attacker is weaker than 50%, it has less than 50% of the nodes, what will happen is that these blocks, which happened in the far past, these blocks were created like an hour before X and Y. These blocks will all be convinced that X precedes Y, because X is part of a cluster of blue nodes that it was created honestly, was published immediately, then it's part of a dense blue set, a dense good set, and therefore they will convince previous blocks that X is a good block, and then we'll have a cascade of the vote until the genesis block, the first block in history. So essentially, the first block in history will determine the vote forever, for all. This block takes a majority of all the DAG, and he also agrees with this majority. And now the new block, which will be created on the right there, it will take the majority on its past. So I haven't said yet how a block that sees both x and y in his past, both x and y in his past votes, then he will take a majority. So he will become blue.
So it can happen that some miners who owns those blocks are no longer working, right? So, but when you say the block, let's say Genesis block in Bitcoin is created Satoshi, and he's not going to vote. So
yeah. So again, it's a good question. These blocks are we don't ask the miner what's its opinion. We don't even ask the block itself. We just consult the structure of the DAG to reason about what this block should vote. We force this block's vote algorithmically. There's no direct communication with anyone about it. It's a local process on my computer, which I run. I take the DAG and I say, here's the Genesis block say, what's its majority? It's just a technical procedure, yeah. Because it's an algorithm, it's a kind of a new creature. It's a consensus algorithm that you run alone and you don't tell anyone about it. That's why it's an interesting framework. Right? I don't need to tell anyone that was the output of the protocol because they see it as well.
So any client and the application do it detached of the...
Yes, that's what I said. It's not a real layer. I just want it for my business to be able to... Yes. Yes.
So remember again, you're doing this coloring to decide about a specific block?
Yes, a specific pair of blocks.
Pair of blocks.
Pairs of...
Which of the pair came first?
Yes. How do I use it for full order? I will touch this shortly. Okay, so yes.
Does this remain scalable when your
What?
graph grows? Your graph will grow at some point, right?
Yes.
Does this remain scalable? You still need to compute that all the time.
Yes. So we have efficient implementations for that. Itai Gerai is a student, undergrad student here, an excellent student. He's writing an efficient implementation of this. So I hope it will be available in GitHub sometime soon. So our aspiration is that the computation will be a constant in the width of the DAG. Okay. So pushing forward, what does Spectre achieve? After this grandiose framework, Spectre does not achieve all the desired properties in the strict sense. So safety, the order does become irreversible after a few seconds. Blocks cannot cut in line. So if you withheld your block, then you will be later in the order. However, with respect to liveness, then two blocks that were created at about the same, that were published, sorry, at about the same time, I can hypothetically execute an attack that balances them forever. Okay, so we call this the weak liveness property. Only if you withheld your block, then the order will be determined robustly. Otherwise, the order is balanceable. You can make it non-robust. But we claim that this is a good enough property for the payment application.
Can you repeat that? I didn't understand.
Yes. So you can create a linear order of the DAG using this pairwise order. However, it will become robust only with respect to blocks that were of this sort, right? There's X and Y. You see it took time for Y to be published. And in this case, Y will succeed X. It will lose to X in a robust manner. Yeah?
Robust
meaning when Y will be published, the attacker won't be able to create many blocks to manipulate it and claim that Y comes before X. Everyone will agree that X comes before Y. However, if you take a block that was published in time proximity to X, it is possible hypothetically to balance them forever. It's a hypothetical attack, but we want to be frank about what we do achieve, what we do not achieve. Okay? So
doesn't that mean that you break the safety?
No. So let me go back. Let me argue why this preserves safety, but does not achieve strict liveness. So safety. Let's say Alice transacts with Bob, and Bob wants to pay Alice. So Bob publishes a transaction to the blockchain in our paradigm, to the block there. So similarly to Bitcoin, Alice won't accept this transaction immediately, right? Alice waits for a few confirmations. In Bitcoin, 60 minutes. And our framework is a few seconds. But nonetheless, Alice will wait for the ledger to build more additional blocks atop the transaction. Now, if during this time the attacker publishes a double spend, another block with a double spend, then Bob will see that and won't confirm the transaction. He will tell Alice, I see a double spend, take your money back or do with it whatever you want. I can't let you take whatever you purchased. Right? So it's very similar to Bitcoin. Also in Bitcoin, you have, when you swipe your Bitcoin credit card, the merchant waits for a few tens of minutes before confirming. So also here. Okay, so that's why safety is guaranteed.
Yeah, but if you wait like, I don't know, 10 more minutes and suddenly the order changes, so now
no, so the property...
The second receiver gets the money and the first one is double spent and ignores it.
No, so the property we guarantee is that after a few seconds that you formally, take the blue block, the set of blocks that can ever precede the blue block closes very fast, in a matter of seconds. So any block that wasn't published within seconds after the blue block was published will never precede it. And the probability is exponentially decaying, like in Bitcoin. Okay, so that's a formal guarantee, and we prove it with great care. But with respect to liveness, again, two blocks that were generally published at the same time, I don't guarantee that. But again, this doesn't harm honest users. Honest payers won't double spend visibly and won't create visibly double spends, so they won't harm their funds. Okay, more questions about this? This is a subtle consensus property. Okay, so again, the guarantee is that as long as our Waldo acquires less than 50% of the computational resources, then blocks that it withholds succeed in the order, will lose in the order to honest blocks. Okay, so importantly, Spectre remains secure regardless of network parameters. It is always converging, always the aforementioned property is satisfied. Again, you only need to suppress the throughput to not congest the network. So this is what we set out to achieve. Of course, there are more hardware considerations. I don't have time to get into this now. Maybe others will pick up this challenge.
Question. You talk about there is no network delays and stuff.
Okay.
I mean, I know that it's asynchronous communication is a theoretical model, but there you would have required 2/3 majority, right? So if you assume there is no delay, but I think inherently you are assuming some eventual synchrony or whatever.
So okay, so it's a good question. So traditionally, you require 2/3 of good nodes. We only need for 51% of good nodes. So we break this threshold. And you're asking about synchronicity. So maybe I have no. Okay, so remember the network layer and the user application layer. The user, when it wants to reason about the robustness of the DAG, it needs to assume some upper bound on the delay diameter of the network. But it's its own belief. It doesn't need to convince anyone about the correctness of this belief. It's not a consensus. It's not hard-coded in the protocol. It's its own belief. It can adjust it as the network shifts, network condition shifts. So it's like the partial synchronous model of consensus protocols. That when you want to analyze the protocol, you do need to assume some bound. So when the user, the application, wants to analyze whether the payment is robustly his own or not, it does need to introduce his own belief on the delay diameter. But in Bitcoin, this diameter is encoded, hard-coded inside the protocol, right? 10 minutes is the assumption that inside the protocol, right? That's the main difference. Okay, so starting to wrap up, I'll just briefly go over Spectre's scalability properties. So again, how scalable is Spectre depends on the bandwidth, and it's not here, but also storage or other considerations, hardware considerations you have. So if you want to achieve 2,000 transactions per second, assuming half a kilobyte per transaction for the sake of this talk, then you need to require nodes to support 1 megabyte per second. But if you're willing to require nodes to support 5 megabytes per second, then you can increase the throughput. Okay, and again, maybe you can support 100,000 transactions per second. But again, this will require 50 megabytes of bandwidth. So you decide what's your network capacity, and then Spectre will be secure, and this will dictate the throughput. This is the correct design of blockchain. The data layer is only limited by the bottom layer, the network layer. And the protocol never introduces a new barrier. Okay? I'll skip these graphs. This shows just that you get a good robustness and very fast. There's also other properties. There's a better fairness because all blocks are rewarded. There's no discrimination between off-chain and on-chain blocks. All blocks are somewhat equal. And just concluding, what's our research path? What do we think can be more achieved further? So first of all, of course, we would want to get rid of the weak liveness property, and we want to make it strict. Whether it's possible or not, we're not sure. Maybe there's some impossibility here that you can't you can't mimic a real consensus without introducing an explicit network delay parameter into the protocol. It corresponds with previous works from the 80s and 90s.
All different thresholds.
What?
All different thresholds.
Or different thresholds. You mean like from the 1/2 to 1/3?
Yes.
Yes. So maybe, again, Spectre achieves resilient to 50% attacks. Maybe we can't achieve that if you want full order. Storage. If you want to utilize your entire bandwidth, let's say every bit is an efficient bit of information, then if you want to utilize all your bandwidth and you have 1 megabyte per second, it's roughly 86 gigabyte per day to store. Who will store these nodes? So Aniket hinted there might be thin clients and pruned full nodes and archive nodes or whatever. It's a good question how to design the system. Again, as Aniket mentioned, when you want to introduce privacy measures, then they introduce new burden on the network, on the storage. Confidential transactions about 2 kilobytes of unused information. And perhaps, and another thing in our path is to think how to adjust these ideas and this agenda to non-proof of work based protocols. So for instance, proof of stake, which Yossi will present today, I think, does not require computation in order to create blocks. It will be interesting to see whether you can use the same ideas to scale up these systems. And finally, just to wrap this up, the take-home message from this line of work is that scalability should depend on the network, and block DAGs are inherently compliant with this framework and are scalable. Spectre is just one way to do this. Maybe there are others. We're definitely working on it. Okay, thank you.